It's not magic, it's science.
Hi everyone, and welcome back to iScience, coming to you from the CEC in the iScience studios. I'm your host, Dr. Donald White, and I think you're going to find that today's episode sounds really good because we're going to focus on sound. Now, sound is really interesting. Sound is a mechanical wave. That means it has to have a material that it passes through. And the waves go through at regular intervals. We call that the frequency. The distance between the waves is the wavelength, and the height of the wave is the amplitude. Now, on Earth, sound travels at sea level at around 760 miles per hour, which is really fast. So you can think about it this way. When lightning strikes and you see the flash, for every 5 seconds that goes by between the flash and the time you hear the thunder, that will give you a mile, that the lightning strike was a mile away. So think about that. So when you see the lightning flash, count to 5, and for every 5 that you count to, that's 1 mile that sound has traveled. So that's pretty fun. Now, the denser the material, the faster sound travels. Sound travels about 5 times faster in water than it does in air. And it travels in really dense materials like steel or metals. It can travel as fast as 13,000 miles per hour, which is crazy fast. Now, I want to show you some of this example here so you can see how the wave actually moves. And to do that, I got to go to the void, and I'm going to get my Newton's cradle. So this is Newton's cradle, and you guys have probably seen this before, right? So you got fishing line that is holding up these little metal balls, and when I pull one of the metal balls out, that classic demonstration starts, all right? And you see this going back and forth. What's actually happening is the energy from this ball is being transferred through these balls to the one on the end. The more energy we transfer, we put in, the more energy is transferred out. So you can see there, we've got 2 balls that are moving back and forth rather than just one. I can also do it with 3, I think. Yep. So that is just the transfer of energy, right? And that's what's happening in a sound wave. The sound wave is actually the molecules of the material bumping into each other. So imagine that this is a molecule of air, and it bumps into another molecule of air and transfers its energy to another one, which flies off, which smacks you in the ear, which transfers its energy to you. So let me show you another example of this. Going to go back to the void and get our tuning forks. And I need a bowl of water. So for this demonstration, I'm going to use a tuning fork. Now, tuning forks are tuned to a particular frequency, which means a particular set of vibrations per second. This tuning fork is set to C, which is 256 hertz, or 256 vibrations per second. Now, it's hard to see when I tap it on the table. The tuning fork is actually vibrating. The tines are vibrating back and forth, but you can't really see that very well. Even if I bring in something that's moving a little bit faster, like this is D, which is 288 hertz. And so when I tap this, that has a higher frequency than this one does, and you can tell it's got a higher frequency because it's shorter than the lower frequency one. But you still can't see anything. You can only hear the difference. So what I want to show you is I want to show you the actual impact of the sound waves, the vibrations coming from the tuning fork on something that we should be able to see a little bit easier. So I'm going to dip it in the water here, and you guys watch closely. You can actually see when I stick the tuning fork in the water, it actually causes ripples in the water. And actually flings some of the water out. Now let's see if I can do it with the lower frequency, or the higher frequency one. Let's see if we get a different effect. You can see it scatters the water everywhere. And that's because the tines on the tuning fork are vibrating back and forth, pushing the water molecules out of the way, which causes it to splash everywhere. So you can really see that sound is a vibration. Now, I want to show you another demonstration. All right, so you guys have seen when somebody sucks the helium out of a balloon, it makes their voice go higher pitched. And that's because the helium goes down into your voice box. The sound waves that come out of your voice box speed up because they're moving through that less dense material, and it moves the sound waves a lot faster. So I'll demonstrate now for you.
So you can hear my voice has definitely changed pitch.
As I keep talking, the helium that is in my voice box will be replaced by the air, and my voice will get back to its normal pitch. Now, that's with helium, and helium is less dense than air. Let me show you what happens when we use the sulfur hexafluoride. Now remember, we said it's more dense than air. So the sound waves that are going to be coming through my voice box are going to run into that denser gas, and they're going to have to slow down. So it's going to be interesting to see what happens here.
So now my voice sounds a little bit different, and that's because the sulfur hexafluoride is so much deeper and denser that the sound that's coming through there, now you can hear my voice going back as it's being pushed out, but you can hear the changes in pitch, and that's all because of the type of material that it's going through. This is way, way denser than the helium balloon. So just a lot of fun to see the difference in speeds that sound. It's a lot of fun to see the difference in speeds of sound through the different materials that you've got. So sulfur hexafluoride is a lot of fun to play with. I also brought another demonstration I'd like to show you that's a lot of fun to play with too. Let me show you what I'm talking about here. Our next demonstration is the Rubens tube.
All right, so after a little bit of setup, I've got for you a Rubens tube. Now, the Rubens tube was first demonstrated by German physicist Heinrich Rubin in the early 1900s. And what it demonstrates is a standing wave. It's just like a musical instrument. As the air moves down the tube, it vibrates, causing the tube to resonate. Now, what you're seeing here are flames of a flammable gas coming out that are going to replicate our wave for us. Now, if I play a tone, this one is a particular frequency, 440 hertz, you can see the standing wave form. You can see the wave valleys, the wave peaks, you can see the wave length, you can see the amplitude of the waves. If I change the frequency, you can see some different behaviors here too. Now you can see that our wavelength has gotten longer because the frequency has gotten lower. Our amplitude has gotten higher on the ends. If I move the frequency up a little bit, you'll see that we can actually move the wave peaks around down the tube. Now again, this is because the tube is vibrating with the frequency of the sound moving through it. This computer speaker over here is actually generating all the sound for us. Now, if we want to get a little bit funky, we can try out some tunes here. Let's try this. So you can see the flames push up, their amplitude increases. That's as the speaker pushes the air down the tube, squeezing the gas out just a little bit more, causing the flames to get a little bit higher. As this plays through, you'll see as the beat hits, you'll see that the flames change height. You can also see the flame, the wave actually moved down the tube here as it goes from the left side to the right side, and then bounces off the end and goes back. So this is a fascinating, fascinating piece of equipment and a fascinating phenomenon. I hope that today's episode sounded good to you. It sure sounded good to me. And I want to invite you back again real soon for another episode of iScience.
This has been an original production for the CEC Network.